Hi there. So last week we were looking at probability distributions, and now we're going to look at a very specific one called the binomial distribution. It's related to binomial expansion, and it's for a specific kind of area wherever you've got an event that can happen which can only have exactly two outcomes. It's either one or the other. So let's have a little look at how they work. Right, now there are four things that have to be true before you can use a binomial distribution. So you might want to make a note of this. It comes up quite a lot. Number one is you've got to have a fixed number of trials. And we talk about a binomial distribution in this terms. In fact, normally you'd have x can be represented in a binomial distribution with n being the number of trials. It's got to be a certain number, and p being the probability of success, which will always be the same. Every trial that happens will be independent of each other. Every trial will have exactly the same probability, and also there have to be exactly two possible outcomes, which we can look at as being success or failure, and those two things will obviously add up to 1. So how might that look? Well, let's have a totally imaginary scenario. You might have two people. You might have a boy and a girl, both beginning with A. Who might that be? That might be someone called Austin, and it might be called someone called Amy. And they might decide that they're going to play a series of 5 games of chess. And it may be known that Amy wins on the probability that Amy wins might be equal to, or it might be 0.6, because she might be just a little bit better than Austin, or maybe just does better when she's playing him. So Austin would be 0.4, but we wouldn't worry about that as such. And I might want to know, what is the probability that out of the 5 games they play, Amy wins exactly 2 of them? Or no, let's just say exactly 1 of them. Let's say Austin has a really good day. What's the probability he wins exactly 1 of them? Well, we could think about that, couldn't we? One of them, it could be the first one that Amy wins. So if that was the case and there were 5 things, you would have to do 0.6 times 0.4 for the first 2, and then Austin would have to keep on winning until we'd had 5 games altogether. So he would have to win 4 times in a row. Or we could think about this as being the probability that Amy wins and the probability that Amy loses. So that would have to happen, wouldn't it? And we'd put that into our calculator as 0.6 times 0.4 to the power of 4, and that would be equal to 0.1536. But that's the chance that she just wins the first one and then loses all the others. Austin might win the first one and she might win the second, in which case it would look like that. Now the chance of that happening is the same as that one, isn't it? But it also might be the 3rd one that she wins, or the 4th one, or the 5th one. So she would actually have 5 times that as a way of, so she would have 5 times that as a way of winning. And if I times that by 5, that does give me the actual probability, which would be 0.0768. So not very likely that she would only win 1 game, and that's what would happen. Now, we could also ask, well, what would be the probability that she would win 2? Now, there's going to be a lot more of that. One way you could think of that is as there being 0.6 squared times 0.4 cubed. Now, that would be one way that it would happen. But how many combinations are there? Well, this is where the binomial expansion comes in, if you remember that. And if we use our calculator, and I'll come out of Well, it normally looks like that, doesn't it? What we would need is we would want to do, we've got 5 games, choosing, winning 2 of them, and then we would multiply that by 0.6 squared times by 0.4 cubed. Now 5 choose 2, how do we do that? We go to option, don't we? And then press the arrow and we get the probability. So it's NCR. So 5 choose 2. The one we did before was 5 choose 1, which is just 5. If I do 5 choose 2, that actually gives me 10, doesn't it? So it's going to be 10 times whatever that is. So times 0.6 squared times 0.4 to the power 3. And that would give us more chance of that happening, 0.2304. And we could work out all the other things there. And there are all sorts of problems that we can solve in that way. So let's move on and have a go at 3 exam style practice questions. So here's our first question. Pause the video, give it a go. So we've got the probability that a switch is faulty of being 0.08, and we're going to have 10 switches that we're looking at. So a suitable distribution to model would be a binomial distribution, and we need to justify the choice. And we can say our binomial distribution would look like this, with the probability, so the number of trials first being 10, the probability being 0.08, and we would say that we could have the binomial distribution because of those 4 things that we said before, which were that you've just got exactly 2 things that can happen, either faulty or not faulty. You've got a set number of trials happening, which is 10. Each probability each time is the same because they're independent of each other. So that's all we need. Now we come to the real part, the probability that the sample contains exactly 4 faulty switches. So we're going to use this, aren't we? And we're going to say the probability that x equals 2, we get 2 faulty switches, is going to be 10 switches, choosing 4 faulty switches times the probability that it is faulty is 0.08, and we want that to happen 4 times. So that means that we want them not to be faulty to happen 6 times. And 8 and 92 make 100, so 0.92 to the power 6. Pump that into the calculator and you should get 0.00522 to 3 significant figures. So here's another question. Pause the video, give it a go. So the assumptions that you have, much as we had before. So we've got the fact that you've just got two things that are possible. Either the genetic marker is present or it's not. You've got each person in the distribution is independent of the other, so the probability is the same every time. And also we're going to have a fixed number of trials, which will be that size n. Next up, using the model, we've got to find the probability of exactly 6 people having this marker. So we are looking at a binomial model of, first of all, the sample size is 50, and the probability of the genetic marker is just 4%, 0.04. So then we are looking, we've got 50, so it's 50 choose 6 multiplied by 0.04, and we want 6 of those, and then that has to be multiplied by the rest of the sample being not having the genetic marker, so that'll be 0.96 because those two add up to 1, and then 6 and 44 add up to 50. Pump that into the calculator and you should get 0.0108. Okay, one more example to go. So here it is. Pause the video and give it a go. The assumptions, as before, should look something like. Then the probability that Hannah rolls exactly 4 6s. So what have we got? We've got 15 trials, and we've got a probability of 0.3 for a 6. So it's 15 choose 4 times 0.3 is happening 4 times, times the other thing that can happen, 0.7, happening 15 take 4 is 11. Put that into the calculator and you should get 0.219 to 3 significant figures. Then the probability she rolls fewer 2 or fewer 6s, so that is 2 or 1 or 0, and you can't really do a really easy one take another. That is 3 different possibilities, isn't it? So you're gonna have to work out the 3 different things and then add them to each other. So you can write all 3 different things out in one go, stick them in brackets if you like, and then add them together to get your result. Should look something like. And there it is. So here's the probability of getting no 6s plus the probability of getting 1 and 2. And notice the powers here, 0 and 15 add up to 15, 1 and 14 add up to 15, 2 and 13 add up to 15, and the number that we're choosing is the same as the probability of what we're calling success. Okay, that's it for this time. See you all next time. Cheerio.